Right at the center of our galaxy, the Milky Way, there is something so powerful that nothing can escape from it. For many years, scientists watched stars spinning in superfast circles around an invisible point in space. What seemed to be just an empty and dark place turned out to be a giant black hole called Sagittarius, a star. This black hole has the mass of 4 million suns altogether, and it sits 26,000 light-years away from us. In 2022, for the first time in history, scientists managed to take a real picture of this monster using telescopes from all over the world working together. Get ready to fall asleep while listening to this video and discover what happens when you approach the event horizon, the place where not even light can come back. Does time really stop passing in this scary place, like Einstein said it would? Subscribe to the channel. Leave your like and comment from which part of the world you are watching. Get comfortable and relax. Let's begin. Have you ever wondered what lies at the very heart of our galaxy? For thousands of years, humans looked up at the night sky without knowing that at the center of our Milky Way lurks one of the most extreme objects in the universe. The story of how we discovered this cosmic monster is a fascinating journey spanning nearly a century of scientific detective work. The discovery of Sagittarius A star began in the 1930s when an engineer named Carl Jansky was investigating sources of static for Bell Telephone Laboratories. Using a large antenna designed to detect radio waves at a wavelength of about 14.5 meters, Jansky noticed something unexpected: radio signals coming from the constellation Sagittarius in the direction of the galactic center. This was the first time anyone had detected radio waves from beyond our solar system, effectively giving birth to the field of radio astronomy. However, the significance of this discovery wasn't immediately recognized. It took another decade before Grota Reber, an amateur astronomer inspired by Jansky's work, built the first dedicated radio telescope in his backyard and confirmed these radio emissions from the galactic center. The scientific community began to take notice, but the limitations of early radio telescopes meant that the source remained frustratingly blurry. The 1950s and 60s saw rapid advancements in radio astronomy technology, as instruments became more sensitive and offered better resolution. Astronomers could begin to distinguish different radio sources within the galactic center region. In 1951, Australian scientists identified several distinct radio sources in this area, designating them as Sagittarius A, B. and C. Sagittarius A appeared to be located precisely at the center of the galaxy, making it particularly intriguing. The real breakthrough came in the 1970s. In 1974, astronomers Bruce Ballack and Robert Brown used the Green Bank interferometer to observe the galactic center at high resolution. They detected a particularly bright, compact radio source within the larger Sagittarius A complex. To distinguish it from the surrounding area, they named it Sagittarius A star, with the asterisk following mathematical convention for denoting a special status. This unassuming name would later become famous as our galaxy's central black hole. Still, nobody knew for certain what Sagittarius A star actually was. The compact radio source was unusual, but there were multiple possible explanations. It could have been a cluster of stars, a cloud of hot gas, or perhaps something more exotic. The idea that it might be a supermassive black hole was considered, but remained speculative without more evidence. The smoking gun came from studying the motion of stars near the galactic center. Beginning in the 1990s, two independent teams of astronomers, one led by Andrea Ghez at UCLA using the Keck Observatory in Hawaii, and another by Reinhard Genzel at the Max Planck Institute using the Very Large Telescope in Chile, began tracking individual stars in the vicinity of Sagittarius A star. This required extraordinary technological finesse. As the galactic center is obscured by dust clouds that block visible light, the astronomers used infrared observations, which can penetrate the dust, combined with adaptive optics to overcome the blurring effects of Earth's atmosphere. what they found was astonishing. Stars near Sagittarius. A star were moving at incredible speeds, some at more than 4,000 kilometers per second. One star, designated S2, follows an elliptical orbit that brings it extraordinarily close to Sagittarius, a star, every 16 years. By tracking these stellar orbits over many years, astronomers could apply Kepler's laws of planetary motion to calculate the mass of the invisible object influencing these stars. The results were clear. Something with the mass of approximately 4 million suns was concentrated in a region smaller than our solar system. Nothing but a supermassive black hole could explain these observations. No collection of stars, neutron stars, or other conventional objects could pack so much mass into such a tiny volume without collapsing. The evidence was so compelling that in 2020, Gers and Genzel were awarded the Nobel Prize in Physics for their work demonstrating the existence of a supermassive black hole at the center of our galaxy. The final chapter in this story of discovery came in 2022, when the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. This remarkable achievement used radio telescopes across the globe working together as an Earth-sized virtual telescope to capture the shadow and glowing ring of material around our galaxy's central black hole. After nearly a century since Jansky first detected radio waves from the galactic center, we could finally see the black hole lurking there. The discovery of Sagittarius A star represents one of the most significant achievements in modern astronomy. It transformed our understanding of galaxies, confirming that supermassive black holes likely reside at the center of most, if not all, large galaxies throughout the universe. The journey from mysterious radio source to confirmed black hole demonstrates how science advances through technological innovation, meticulous observation, and the gradual elimination of alternative explanations until only one possibility remains. Today, astronomers continue to study Sagittarius A star to learn more about how supermassive black holes form, grow, and influence their surroundings. Every new observation brings fresh insights into this cosmic giant that silently shapes our galactic home from its central throne. 4 million times more massive than our Sun, yet hidden from direct view until just recently. The physical properties and dimensions of the black hole. Imagine an object with the mass of 4 million suns packed into a region smaller than our solar system. It sounds like science fiction, but this is precisely what sits at the heart of our galaxy. Sagittarius A star defies our everyday intuition about how matter behaves, representing one of the most extreme environments in the universe. Let's explore what makes this cosmic monster so extraordinary. At its most fundamental level, Sagittarius A star is defined by its mass. Astronomical measurements have determined that it contains approximately 4.3 million solar masses. This incredible concentration of matter warps the fabric of space-time so severely that it creates a region from which nothing, not even light, can escape, the defining characteristic of a black hole. To put this mass in perspective, if you could replace our Sun with Sagittarius, a star, it would be as if you substituted a basketball with something weighing as much as Mount Everest. Despite its enormous mass, Sagittarius A star is surprisingly compact. The boundary marking the point of no return, called the Event Horizon, has a radius of just around 12 million kilometers. While this might sound huge, it's merely about 8 times the size of our Sun, or about 25 times the distance from Earth to the Moon. If placed at the center of our solar system, the Event Horizon would fit comfortably inside Mercury's orbit. This extreme density is what makes black holes so extraordinary. They represent the ultimate compression of matter into an incredibly small volume. One common misconception is that black holes act like cosmic vacuum cleaners, sucking in everything around them. In reality, Sagittarius. A star doesn't pull on distant objects any more strongly than a normal star of the same mass would. if our Sun were magically replaced by a black hole of identical mass. Earth's orbit would remain unchanged. The difference is what happens when you get very close to a black hole. The gravitational forces become so extreme that nothing can escape once it crosses the event horizon. Interestingly, Sagittarius, A star, is relatively quiet compared to black holes at the centres of many other galaxies. It's currently in a dormant phase, consuming very little of the surrounding material. Scientists estimate it's accreting matter at a rate less than 1/10,000,000th of what would be expected given its mass. If it were actively feeding, it would shine brilliantly across multiple wavelengths of light as the infalling material heated up to millions of degrees. Instead, it glows relatively dimly, primarily in radio wavelengths, with occasional flares in X-ray and infrared. Beyond the event horizon lies what theorists call the singularity, a point where our current understanding of physics breaks down. According to Einstein's theory of general relativity, all of Sagittarius A's mass is compressed into an infinitely dense point at its centre. Many physicists believe this mathematical infinity is a sign that we need a quantum theory of gravity to fully understand what happens there. Until such a theory is developed, the true nature of the singularity remains one of the greatest mysteries in physics. Another fascinating property of Sagittarius A star is its spin. Just as Earth rotates on its axis, black holes can spin as well, and this rotation has profound effects on the surrounding space-time. When a black hole spins, it drags the fabric of space-time around with it, a phenomenon called frame dragging. Based on observations of material orbiting Sagittarius A star, astronomers believe it is indeed rotating, though measuring the precise rate of this spin remains challenging. A spinning black hole creates a region outside the event horizon called the ergosphere, where nothing can remain stationary. Space itself is in motion. The extreme gravity near Sagittarius, a star, creates other remarkable effects predicted by Einstein's theories. Time itself flows differently near the black hole, a phenomenon called gravitational time dilation. If you could somehow survive near the event horizon, you would experience time passing normally from your perspective, but an outside observer would see your clock ticking much more slowly. This isn't just theoretical. The precise orbits of stars around Sagittarius A star have allowed astronomers to measure these relativistic effects directly. Light behaves strangely near Sagittarius A star as well. The intense gravitational field bends light paths significantly, creating what astronomers call gravitational lensing. This bending is so extreme near the event horizon that light can actually orbit the black hole multiple times before either escaping to distant observers or falling in. This creates the distinctive bright ring seen in the Event Horizon Telescope image, where photons from behind the black hole are bent around it toward our telescopes. The environment immediately surrounding Sagittarius A star is among the most violent and energetic regions in our galaxy. Material spiraling toward the black hole forms an accretion disk that heats up to millions of degrees through friction and compression. This superheated plasma emits radiation across the electromagnetic spectrum and can generate powerful magnetic fields. Occasionally, magnetic reconnection events, similar to solar flares but far more powerful, cause bright outbursts from the vicinity of the black hole. Scientists are particularly interested in understanding the boundary region just outside the event horizon. This is where infalling material makes its final plunge, accelerating to nearly the speed of light. The physics in this region involves extreme temperatures, strong magnetic fields, and relativistic effects that can't be replicated in any laboratory on Earth. By studying this environment around Sagittarius A star, astronomers gain insights into the behavior of matter under the most extreme conditions found in nature. What makes Sagittarius A star especially valuable to science is its proximity to Earth. At just 26,000 light-years away, it's the closest supermassive black hole we can study. Despite being 4 million times more massive than our Sun, It's actually quite small compared to black holes in other galaxies, which can reach billions of solar masses. This combination of proximity and moderate size makes Sagittarius A star an ideal laboratory for testing our theories about black hole physics. Understanding the physical properties of Sagittarius A star isn't just an academic exercise, it helps answer fundamental questions about the universe. How do galaxies and their central black holes co-evolve? What role do supermassive black holes play in galactic development? And perhaps most profoundly, how do the extreme conditions near black holes help us reconcile Einstein's theory of general relativity with quantum mechanics? As we continue to observe and model Sagittarius A star, we inch closer to answering these cosmic questions. As our understanding of Sagittarius A star continues to deepen, one of the most remarkable achievements in modern astronomy has been our ability to actually see this cosmic behemoth. The journey from theoretical concept to visible reality represents one of science's greatest triumphs, requiring international collaboration and technological innovation on an unprecedented scale. The Event Horizon Telescope project emerged from a simple but audacious idea. If we could somehow link radio telescopes across the entire planet to work as a single instrument, we might capture enough detail to actually see a black hole's shadow. This technique, called Very Long Baseline Interferometry, VLBI, effectively creates a virtual telescope the size of Earth itself. While astronomers had used VLBI for decades to study compact radio sources, the technical challenges of coordinating global observations precisely enough to image a black hole seemed insurmountable until recently. The collaboration began taking shape in the early 2000s, with radio astronomers gradually developing the specialized equipment and techniques needed for such precise observations. By 2017, the project had grown to include 8 radio observatories spread across locations as diverse as Hawaii, Chile, Mexico, Spain, Arizona, and even Antarctica. Each telescope needed to be synchronized with atomic clock precision and configured to collect data at exactly 1.3 millimeters wavelength, chosen because it could penetrate the dust and gas surrounding Sagittarius A star while still providing sufficient resolution to see its structure. When the Event Horizon Telescope conducted its groundbreaking observations in April 2017, the process resembled a carefully orchestrated global symphony. Each telescope had to be pointed at Sagittarius A star simultaneously, with local weather conditions favourable at all sites, a rare alignment that only allowed for a few days of observation. The amount of data generated was staggering, several petabytes, too massive to transfer over the internet. Instead, hard drives had to be physically shipped from each telescope to central processing facilities at the Max Planck Institute in Germany and MIT Haystack Observatory in Massachusetts. Processing this mountain of data required supercomputers and entirely new algorithms. The challenge wasn't just computational, but conceptual. How do you combine observations from telescopes with different characteristics, accounting for Earth's rotation, atmospheric interference, and countless other variables? The team developed a novel approach called regularized maximum likelihood, which essentially tests countless possible image configurations against the data to find the most likely appearance of Sagittarius A star. Meanwhile, the scientific world waited with bated breath. Rumours spread that the Event Horizon Telescope had actually succeeded in imaging a black hole, but the team maintained silence while meticulously verifying their results. The first breakthrough came in April 2019, when the collaboration revealed the first ever image of a black hole, but it wasn't Sagittarius A star. Instead, they showed us M87 star, the supermassive black hole at the centre of the Messier 87 galaxy, 55 million light-years away. Despite being much farther than Sagittarius A star, M87 star is over 1,000 times more massive, making its event horizon appear roughly the same size in our sky and actually easier to image because it changes more slowly. The team continued working on the more challenging Sagittarius A star data, wrestling with the fact that our galaxy's black hole changes on timescales of minutes rather than days. This meant the black hole's appearance shifted during the very observations meant to capture it, like trying to photograph a child who won't sit still. Finally, on May 12th, 2022, the world got its first look at our galaxy's central black hole. The image revealed a glowing, ring-like structure with a central dark region, the shadow of Sagittarius, a star itself. What makes this achievement so remarkable is the scale involved. Imaging Sagittarius, a star from Earth, is equivalent to photographing a donut on the Moon's surface, an object billions of times smaller than what conventional telescopes can resolve. The image confirmed several key predictions from Einstein's general relativity, including the roughly circular appearance of the photon ring and the overall size matching theoretical calculations. The Event Horizon Telescope continues to improve its capabilities, adding more telescopes to the network and developing more sophisticated data processing techniques. Future observations aim to produce not just static images but movies showing how material moves around Sagittarius A star in real time. These improvements may soon allow astronomers to observe the detailed structure of the jets sometimes emitted by active black holes and better understand how Sagittarius A star interacts with its surroundings. Perhaps most significantly, the image of Sagittarius A star transformed something once purely theoretical into an observable reality. For decades, black holes existed as mathematical solutions to Einstein's equations and as invisible gravitational influences. Now we can actually see one, confirming that these extreme objects truly exist exactly as theory predicted. The glowing ring around Sagittarius A star's shadow has become an iconic image, joining the ranks of the Apollo Earthrise photo and the Hubble Deep Field as one of astronomy's most profound and perspective-changing views of our universe. While the Event Horizon Telescope gave us our first direct glimpse of Sagittarius A star, much of what we know about this black hole comes from studying the stars that orbit it. These stellar dancers have revealed crucial information about Sagittarius A's mass, location, and nature through their gravitational interactions with the invisible giant. The centre of our galaxy is an extraordinarily crowded place. Within the central parsec, about 3.26 light-years, there exists a dense cluster of stars, unlike anywhere else in the Milky Way. Some of these stars, particularly those closest to Sagittarius A star, follow trajectories that provide astronomers with a natural experiment in extreme physics. By tracking their precise movements over many years, scientists have effectively used these stars as test particles to map the gravitational field around our galaxy's central black hole. This stellar monitoring program began in earnest during the 1990s, when advances in adaptive optics, technology that compensates for Earth's atmospheric distortion, allowed astronomers to clearly see individual stars in this crowded region. Two teams took the lead in this research. Andrea Ghez and her colleagues at UCLA using the Keck Observatory in Hawaii, and Reinhard Genzel's team using the Very Large Telescope in Chile. Both groups employed infrared observations to penetrate the dust clouds that block visible light from the galactic center. The most famous star in this celestial ballet is designated S2, or S0-2 in the American naming system. This blue star, about 15 times more massive than our Sun, follows an elliptical orbit that brings it sweeping around Sagittarius A star every 16 years. At its closest approach, called periaps, S2 comes within just 17 light hours of the black hole, about 4 times the distance from our Sun to Neptune. During this close passage, the star reaches speeds of over 7,000 kilometers per second, about 2% of the speed of light. S2's most recent close approach occurred in May 2018, providing astronomers with an exceptional opportunity to test Einstein's theory of general relativity in the strong gravitational field near a supermassive black hole. As predicted by relativity, the star's light showed a gravitational redshift, its wavelength stretched by the black hole's intense gravity. Additionally, The orbit itself displayed the relativistic effect called precession, where the entire elliptical orbit slowly rotates over time, tracing a pattern like a spirograph. Beyond S2, astronomers have now tracked more than 40 stars in the immediate vicinity of Sagittarius A star. Each follows its own elliptical path, collectively resembling a swarm of bees around a central point. These orbits have random orientations in three-dimensional space, confirming that they're responding to a single, spherically symmetric mass concentration, exactly what we'd expect from a black hole. One of the most puzzling aspects of these stars is their age. Many appear to be relatively young, just 10 to 100 million years old, which creates a paradox known as the problem of youth. The powerful tidal forces near Sagittarius. A star should prevent normal star formation, as gas clouds would be torn apart before they could collapse into stars. Astronomers have proposed several explanations for these youthful stars, including the possibility that they formed farther away and migrated inward, or that they resulted from unusual formation mechanisms unique to the extreme environment near the black hole. The very existence of these fast-moving stars provides one of the strongest lines of evidence for the presence of a supermassive black hole. Alternative explanations, such as a dense cluster of neutron stars or stellar mass black holes, have been definitively ruled out by the observed orbital patterns. Only a single, extremely compact object with a mass of about 4 million suns can explain the dance of stars we observe. Particularly intriguing are several stars that appear to have been gravitationally slingshot by close encounters with Sagittarius A star, achieving speeds so great they may eventually escape our galaxy entirely. These hypervelocity stars are astronomical bullets, carrying the imprint of their violent interactions with the central black hole as they race outward through the Milky Way. As observational techniques improve, astronomers have detected increasingly subtle effects in these stellar orbits. Beyond just the positions and velocities of stars, scientists can now measure their accelerations and even the precession of their orbital planes due to the black hole's frame-dragging effect. These measurements allow for increasingly precise determinations of Sagittarius A star's mass and potentially even its spin rate. Future observatories promise even more detailed views of this stellar dance. The Extremely Large Telescope, currently under construction in Chile with a 39-metre primary mirror, will resolve features 10 to 15 times smaller than current instruments can see. This may allow astronomers to detect much fainter stars even closer to Sagittarius A star, possibly including pulsars whose regular radio pulses would provide extraordinarily precise probes of the space-time near the black hole. Together with direct imaging from the Event Horizon Telescope, these stellar orbits provide complementary information about Sagittarius A star. The image shows us the immediate environment around the black hole's event horizon, while the stellar orbits reveal its gravitational influence extending much farther out. Combined, they've transformed our understanding of the dynamic center of our galactic home, replacing earlier speculations with concrete, detailed knowledge of the supermassive black hole lurking there. This central black hole and its surrounding stars continue to serve as an unparalleled natural laboratory for testing fundamental physics under conditions impossible to replicate on Earth. As we develop new observational capabilities and gather longer time series of data on these stellar orbits, Sagittarius A star will undoubtedly continue to reveal new secrets about the nature of gravity, space-time, and the objects that inhabit the extreme environments at the centers of galaxies throughout our universe. While studying the stars orbiting Sagittarius, a star gives us tremendous insight into its gravitational effects. Black holes present one of the most profound puzzles in modern physics when we try to understand them at the quantum level. At the intersection of gravity and quantum mechanics lies a conundrum that has stumped the brightest minds in physics for decades, the black hole information paradox. The problem emerges from a fundamental conflict between two cornerstone theories of physics. On one hand, Einstein's general relativity describes black holes as regions where space-time is so severely curved that nothing can escape once it crosses the event horizon. On the other hand, quantum mechanics insists that information can never be truly destroyed in our universe. When these theories collide at the event horizon of Sagittarius A star, we encounter a profound contradiction that suggests either one or both of these theories must be incomplete. This paradox first gained prominence in the 1970s through the groundbreaking work of Stephen Hawking, in what became known as Hawking radiation. He demonstrated that quantum effects near the event horizon cause black holes to emit particles and slowly evaporate over time. While this discovery was revolutionary, it created a serious problem. If a black hole eventually evaporates completely, what happens to all the information that fell into it throughout its lifetime? According to quantum mechanics, the information describing every particle, its quantum states, properties, and relationships, must be preserved. But Hawking's initial calculations suggested that the radiation emitted by an evaporating black hole would be completely random, effectively scrambling the original information beyond recovery. This contradicts a fundamental principle of quantum theory called unitarity, which requires that information about quantum states must be conserved. To visualize this problem, imagine throwing an encyclopedia into Sagittarius A star. The book contains specific information arranged in a particular order. If the black hole later evaporates through Hawking radiation, quantum mechanics demands that, in principle, someone could reconstruct that encyclopedia from the radiation. But Hawking's original analysis suggested this would be impossible. The radiation would look identical regardless of what fell in, essentially erasing the universe's memory of that encyclopedia forever. This paradox becomes even more acute for Sagittarius A star because of its enormous mass. The larger a black hole, the colder its Hawking radiation and the slower it evaporates. With 4 million solar masses, Sagittarius, a star would take an almost unimaginable time to evaporate, roughly 10 to the power of 87 years, vastly longer than the current age of the universe at 13.8 billion years. This means any information that falls into Sagittarius A star is effectively locked away for a duration exceeding most timescales we can meaningfully comprehend. Several potential solutions to the information paradox have emerged over the years. One approach, championed by Leonard Susskind and others, is called the holographic principle. This theory suggests that information isn't actually lost inside the black hole but is somehow encoded on the event horizon itself, similar to how a two-dimensional hologram can store information about a three-dimensional object. In this view, the event horizon of Sagittarius A star would contain the complete record of everything that has ever fallen into it, preserved in incredibly complex quantum correlations. Another possibility involves quantum entanglement between the interior and exterior of the black hole. When Hawking radiation is emitted, the particles that escape may remain quantum mechanically entangled with the material inside the black hole, potentially preserving information through these quantum connections. Some theories propose that as the black hole approaches the end of its evaporation, a final burst of highly complex radiation might carry away all the remaining information. Perhaps the most radical solution comes from the firewall hypothesis, which suggests that the conflict between general relativity and quantum mechanics creates an energetic wall at the event horizon. According to this controversial idea, anything crossing into Sagittarius A star would be immediately destroyed at the boundary rather than passing smoothly through as general relativity predicts. The black hole information paradox represents one of the most significant clues we have in the search for a unified theory of quantum gravity, a framework that would reconcile general relativity with quantum mechanics. While Sagittarius A star itself is too stable to provide direct observational evidence regarding Hawking radiation or information preservation, it serves as a concrete example that grounds these abstract theoretical discussions. More recently, insights from string theory and ADS/CFT correspondence, a theoretical framework relating gravity to quantum field theories, have suggested that information might be preserved through incredibly subtle quantum correlations in Hawking radiation. These correlations would be practically impossible to detect for a black hole like Sagittarius A star, but they would ensure that information is technically never lost, just scrambled beyond practical recognition. For physicists, the information paradox of black holes isn't just an academic puzzle, it points to a fundamental gap in our understanding of how the universe works at its most basic level. Resolving this paradox may require us to radically revise our concepts of space, time, and information, perhaps even more dramatically than Einstein's theories revised Newton's view of gravity. When we look at the image of Sagittarius A star, we're not just seeing a cosmic object, but a profound question mark challenging our deepest theories about reality. While these quantum considerations might seem detached from the practical business of observing Sagittarius A star, they highlight how black holes serve as crucial theoretical laboratories where our most fundamental physical theories can be tested against each other. The apparently simple dark center we see in the Event Horizon Telescope image actually represents one of the most complex theoretical frontiers in modern physics, moving from these quantum mysteries to more observable phenomena. Let's examine how Sagittarius A star interacts with its surroundings through the process of accretion and jet formation. Unlike the theoretical puzzles of quantum information, these processes produce effects that astronomers can directly detect and study, providing a more tangible window into our galaxy's central black hole. Accretion is the process by which black holes grow, gathering matter from their surroundings into an orbiting disk before it plunges across the event horizon. For Sagittarius, a star, this process is surprisingly subdued compared to many other supermassive black holes throughout the universe. Our galaxy's central black hole is currently in a quiescent phase, accreting material at a rate roughly 100,000 times lower than its theoretical maximum. This relative inactivity presents an interesting puzzle. With millions of stars and vast clouds of gas in the central region of our galaxy, why isn't Sagittarius A star consuming material more voraciously? The answer involves a complex interplay of factors including stellar winds, magnetic fields, and past periods of activity that may have cleared out much of the nearby gas. The material that does make its way towards Sagittarius A star forms an accretion disk, a flattened or rotating structure of gas and dust. As this material spirals inward, friction causes it to heat up to millions of degrees. At these extreme temperatures, the gas becomes ionized into plasma and begins to glow across multiple wavelengths of the electromagnetic spectrum, particularly in X-rays and infrared light. Astronomers regularly monitor this radiation to track Sagittarius A star's feeding habits. What they've found is that our central black hole is anything but steady in its dining. Roughly daily, Sagittarius A star experiences flares, brief periods of increased brightness lasting from minutes to hours, where its X-ray emission can brighten by factors of 10 to 100. These flares likely result from magnetic reconnection events in the accretion disk, similar to solar flares on our Sun, but far more powerful. Beyond these common small flares, historical observations suggest Sagittarius A star has experienced much more dramatic feeding events in the past. Studies of X-ray light echoes, radiation that has bounced off molecular clouds in the galaxy, indicate that Sagittarius A star was hundreds to thousands of times more active just a few hundred years ago. Going back further, evidence suggests that several million years ago, Sagittarius A star may have undergone a truly massive accretion event, possibly consuming an entire gas cloud or even a small star, which produced vast outflows of energy that created huge bubbles of hot gas extending thousands of light years above and below the galactic plane. One of the most important recent discoveries about Sagittarius A star's accretion process came in 2019, when astronomers detected changes in brightness of the infrared emission from its accretion flow. These changes followed a roughly 30-minute cycle, suggesting that hotspots of material were orbiting the black hole at about 30% of the speed of light. This observation provided strong evidence that the accretion disk extends very close to the event horizon, well within the region where relativistic effects dominate. While many active supermassive black holes in other galaxies produce dramatic jets, narrow .d high-energy streams of particles that can extend for thousands or even millions of light years, Sagittarius, a star shows only modest jet activity. Radio observations have detected small, poorly collimated outflows extending a few light years from the black hole. These relatively weak jets align with Sagittarius A star's current low accretion rate, as the power of black hole jets typically correlates strongly with how quickly they're consuming matter. The relatively weak jet from Sagittarius A star still influences its environment. However, the outflowing particles interact with the surrounding interstellar medium, transferring energy and potentially regulating star formation in the central parsecs of the galaxy. This represents a scaled-down version of the feedback process seen in many other galaxies, where central black holes play a crucial role in regulating their host galaxies' evolution through jets and outflows. The modest accretion rate of Sagittarius A star actually proved helpful for the Event Horizon Telescope's imaging efforts. If our galaxy's central black hole were actively feeding like many quasars, the bright emission from the accretion disk might have overwhelmed the subtle details of the black hole shadow. Instead, the relatively low activity allowed the EHT to capture the delicate structure of light bending around the event horizon. What makes accretion onto Sagittarius A star particularly interesting is that we can observe it happening in real time. Changes in the accretion flow occur on timescales of minutes to hours, allowing astronomers to watch the process unfold. This stands in stark contrast to most astronomical phenomena, which typically evolve over thousands to millions of years. Future observations with new facilities like the James Webb Space Telescope promise to reveal even more details about how Sagittarius A star feeds. Higher resolution imagery may show the detailed structure of the accretion disk, potentially even capturing the moment when material makes its final plunge across the event horizon, stretched and heated by the extreme gravitational forces. The modest feeding habits of Sagittarius A star today may not last forever. Astronomers have identified a large cloud of gas called G2 that made a close approach to Sagittarius A star in 2014. While the cloud wasn't completely disrupted as some had predicted, similar encounters in the future could potentially trigger more active feeding periods. Additionally, over much longer timescales of billions of years, our galaxy's inevitable collision with the Andromeda Galaxy could funnel large amounts of gas toward the center, potentially awakening Sagittarius A star from its current slumber and triggering a quasar-like phase of intense accretion and jet activity. Through studying the accretion processes and outflows of Sagittarius A star, astronomers gain insights not just into our own galaxy's central black hole, but into the broader relationship between supermassive black holes and their host galaxies throughout the cosmos. The feeding habits of these cosmic giants play a crucial role in galactic evolution, influencing everything from star formation rates to the temperature and composition of the interstellar medium across billions of years of cosmic history. The dynamic processes of accretion and jet formation around Sagittarius A star occur against the backdrop of one of the most extreme environments in the known universe, a region where space and time themselves behave in ways that defy our everyday intuition. As we approach the event horizon of our galaxy's central black hole, the fabric of space-time becomes distorted to such an extent that Einstein's general relativity reveals its most bizarre and fascinating consequences. At the heart of these distortions is a simple principle with profound implications: mass curves space-time. While we experience this curvature in a mild way through Earth's gravity, near Sagittarius A star the effect becomes so extreme that space and time no longer behave as separate entities, but rather as aspects of a unified four-dimensional structure that becomes severely warped. This warping reaches its maximum at the event horizon, that critical boundary sitting approximately 12 million kilometers from the black hole's center. One of the most counterintuitive effects of this space-time distortion is gravitational time dilation. According to Einstein's equations, time passes more slowly in stronger gravitational fields. Near Sagittarius, a star, this effect becomes dramatic. If you could somehow hover just outside the event horizon, ignoring the fact that the extreme tidal forces would tear you apart, you would experience time passing normally from your perspective. But an observer watching from Earth would see you moving in extreme slow motion. Your clock would appear to tick at a glacial pace compared to theirs. This time dilation effect becomes increasingly pronounced as one approaches the event horizon. At the horizon itself, time dilation becomes infinite from an outside observer's perspective. This creates a remarkable phenomenon. To someone watching from a safe distance, an object falling towards Sagittarius. A star appears to slow down more and more as it approaches the horizon, eventually seeming to freeze at the boundary. The infalling object never actually appears to cross the horizon. Instead, its image becomes increasingly red-shifted and dimmer until it fades from view. Yet from the perspective of the falling object itself, nothing special happens at the horizon crossing. Time continues to flow normally, and the horizon is passed without any local indication of crossing a boundary. This disconnect between the experiences of different observers highlights how radically space-time is distorted in the vicinity of Sagittarius A star. Another fascinating manifestation of space-time distortion near the event horizon involves the paths of light rays. In flat space-time, light always travels in straight lines. But in the severely curved space-time around Sagittarius, a star, light follows curved paths dictated by the geometry of space itself. Some of these paths are particularly special. At a distance of about 1.5 times the event horizon radius, light can actually orbit the black hole in a circular path called a photon sphere. This photon sphere creates remarkable visual effects. Light that comes close to this orbit can circle Sagittarius A star multiple times before either escaping to distant observers or falling into the black hole. This creates what astronomers call the photon ring, a bright circle that appears slightly larger than the shadow of the event horizon itself. This ring is what the Event Horizon Telescope primarily captured in its historic image. The space-time distortions near Sagittarius, a star, also create another striking visual phenomenon: gravitational lensing. Light from sources behind the black hole can be bent around it toward Earth, creating multiple images of the same background object or stretching point sources into arcs. If we could view Sagittarius A star from nearby, these lensing effects would create an extraordinarily warped view of the universe, with the same stars appearing in multiple locations simultaneously, and entire sections of the sky visible that should be hidden behind the black hole. For objects orbiting near Sagittarius A star, these space-time distortions manifest in several observable ways. One is the precession of orbits, unlike planets in our solar system, which follow nearly fixed elliptical paths. Objects orbiting close to Sagittarius A star trace rosette patterns as their entire orbital ellipse rotates with each revolution. The star S2, which comes within 17 light hours of the black hole at its closest approach, displays measurable orbital precession that exactly matches the predictions of general relativity. If Sagittarius A star is rotating, as most astronomers believe, the space-time distortions become even more complex. A spinning black hole drags the fabric of space-time around with it in a process called frame dragging. This creates a region outside the event horizon called the ergosphere, where nothing can remain stationary relative to distant space. The rotation of space-time itself forces everything within this region to rotate in the same direction as the black hole. Perhaps the most extreme space-time distortion associated with black holes is the theoretical presence of a singularity at the center. According to classical general relativity, all of Sagittarius A's mass is concentrated at a single point of infinite density. where space-time curvature becomes infinite and the known laws of physics break down. Most physicists believe this mathematical singularity is not physically real, but rather indicates where our current theories need to be replaced by a quantum theory of gravity. While these space-time distortions sound like science fiction, many have been directly verified through observations. The precession of S2's orbit, gravitational redshift of light from stars near Sagittarius A star, and the size and shape of the shadow seen in the Event Horizon Telescope image all precisely match the predictions of general relativity. These confirmations represent some of the strongest evidence for Einstein's theory in the strong field regime, where the effects of curved space-time are most pronounced. Understanding these distortions is not merely an academic exercise, it has practical implications for interpreting observations of Sagittarius A star. The light we receive from the vicinity of the black hole has been subject to these extreme gravitational effects, meaning that what we see is a distorted representation of the actual physical processes occurring there. Astronomers must carefully account for these distortions when interpreting their observations, essentially unwrapping the effects of curved spacetime to understand the underlying physics. The space-time distortions around Sagittarius A star also provide an opportunity to test alternative theories of gravity. While Einstein's general relativity has passed every experimental test so far, including observations of Sagittarius A star, scientists continue to refine these measurements to look for potential deviations that might point to new physics. As observational techniques improve, Sagittarius A star will serve as an increasingly precise laboratory for testing the fundamental nature of gravity, space, and time. These extreme distortions of space-time don't exist in isolation. They've played a crucial role in shaping the evolution of our entire galaxy. The story of Sagittarius A star is deeply intertwined with the history of the Milky Way itself, with each influencing the development of the other through billions of years of cosmic evolution. When astronomers look at galaxies throughout the universe, they notice something remarkable. There seems to be a consistent relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. Specifically, a galaxy's central black hole typically has a mass about 1,000th that of the galaxy's central bulge of stars. This relationship is so consistent that it cannot be coincidental, suggesting that galaxies and their central black holes must somehow co-evolve, each influencing the growth of the other. In the case of Sagittarius A star and the Milky Way, this co-evolution has played out over more than 13 billion years. The black hole likely began forming in the earliest stages of our galaxy's history, perhaps starting as a smaller seed black hole that was either created from the collapse of a massive star or directly from dense gas in the early universe. As the young Milky Way evolved, this seed black hole grew by accreting surrounding gas and merging with other black holes brought in when the Milky Way absorbed smaller dwarf galaxies. Throughout this history, Sagittarius A star has influenced galactic development in several important ways. During periods of active accretion, the energy released as material fell into the black hole would have heated surrounding gas, potentially regulating star formation in the galaxy's central regions. While Sagittarius A star is relatively quiet today, evidence suggests it has gone through much more active phases in the past, possibly including quasar-like periods where its energy output rivaled that of all stars in the galaxy combined. The strongest evidence for past activity comes from giant bubbles of high-energy particles extending about 25,000 light-years above and below the galactic plane. Discovered by NASA's Fermi Gamma Ray Space Telescope in 2010, these Fermi bubbles appear to have been created by a powerful outburst from the galactic center several million years ago. This event may have been triggered by a large cloud of gas falling into Sagittarius A star, or perhaps by a cluster of stars forming too close to the black hole. During such active periods, Sagittarius A star would have injected enormous amounts of energy into the surrounding interstellar medium through radiation and outflows, heating gas that might otherwise have cooled and collapsed to form stars. This process, known as feedback, represents one of the primary ways that supermassive black holes influence their host galaxies in more massive galaxies than our own. This feedback can be powerful enough to halt star formation entirely, explaining why many massive elliptical galaxies contain primarily old stars. The relationship works in the other direction as well. The Milky Way's evolution has shaped Sagittarius A*'s growth history. The galaxy's spiral structure channels gas into the central regions, providing fuel for the black hole. Major events in galactic history, such as collisions with other galaxies, would have driven gas toward the center, triggering periods of enhanced accretion onto Sagittarius A*. The most dramatic example of this two-way relationship is currently in the making. Approximately 4 billion years from now, the Milky Way will begin colliding with the neighboring Andromeda galaxy. This collision, which will unfold over hundreds of millions of years, will funnel enormous quantities of gas toward the center of the merging system, likely triggering intense activity in both Sagittarius A* and Andromeda's central black hole. Eventually, these two supermassive black holes will themselves merge in a cataclysmic event that will release enormous energy in the form of gravitational waves. Archaeological evidence of past mergers can be seen throughout our galaxy. The Milky Way's halo contains streams of stars that once belonged to smaller galaxies consumed by our own. Each of these merger events would have affected Sagittarius A*, potentially bringing smaller black holes that eventually merged with it and driving waves of gas toward the center that fueled periods of active accretion. Recent studies using data from the Gaia Space Observatory have revealed that the Milky Way experienced a significant merger with a galaxy nicknamed Gaia Enceladus about 10 billion years ago. This collision, which astronomers can reconstruct by analyzing the motion and composition of stars, would have dramatically altered the Milky Way structure and likely triggered substantial activity in Sagittarius A* as gas from the collision funneled toward the galactic center. Even the stars orbiting close to Sagittarius A* today tell a story of galactic evolution. Many of the stars in the central parsec appear to have formed elsewhere and migrated inward, while others show evidence of having formed in place despite the challenging environment. Their chemical composition reflects the history of star formation and element production throughout the galaxy's lifetime. Sagittarius, a star, also influences the Milky Way through its gravitational effects on the surrounding distribution of stars and gas. The black hole's gravity, along with the collective gravity of the dense nuclear star cluster surrounding it, anchors the galaxy's central bulge and influences the overall galactic rotation curve. While dark matter dominates the gravitational effects on larger scales, Sagittarius A* plays a crucial role in shaping the innermost regions of our galaxy. Understanding the connected histories of Sagittarius A* and the Milky Way helps astronomers piece together the overall story of galaxy evolution throughout the universe. By studying our own galaxy's central black hole in detail, scientists can better understand the processes that have shaped millions of other galaxies we observe across cosmic time. This relationship between black holes and their host galaxies represents one of the most important discoveries in modern astronomy, transforming our view of these objects from exotic curiosities to key players in cosmic evolution. The intricate relationship between Sagittarius A* and our galaxy is just one example of how supermassive black holes shape their cosmic neighborhoods. To gain an even deeper understanding of these extraordinary objects, astronomers have found tremendous value in comparing our galactic center with other black holes, particularly M87, the only other supermassive black hole that has been directly imaged to date. These two cosmic giants, despite both being supermassive black holes, display remarkable differences that highlight the diversity of these extreme objects across the universe. M87 resides at the heart of Messier 87, a massive elliptical galaxy in the Virgo cluster, approximately 55 million light-years from Earth. The first striking difference between Sagittarius A* and M87 is their mass. While Sagittarius A star contains about 4.3 million solar masses, M87 star is truly colossal, containing roughly 6.5 billion solar masses, making it approximately 1,500 times more massive than our galaxy's central black hole. This enormous difference in mass is reflected in the size of their event horizons. M87's event horizon has a radius of about 120 billion kilometers, roughly 20 times the diameter of our entire solar system. Despite M87 being much farther away than Sagittarius A, 55 million light-years compared to a mere 26,000 light-years, both black holes appear approximately the same size in the sky as viewed from Earth. This cosmic coincidence made it possible for the Event Horizon Telescope to capture both with similar resolution, though the imaging processes faced different challenges for each target. The environment surrounding these two black holes differs dramatically as well. M87 star is currently in an active feeding phase, vigorously consuming surrounding matter and producing spectacular effects. It generates an enormous relativistic jet of particles that extends more than 5,000 light-years from the galaxy's center. This jet, propelled to nearly the speed of light by intense magnetic fields around the black hole, is one of the most dramatic features in the nearby universe. In contrast, Sagittarius A star is relatively quiet, producing only modest outflows and weak jets that extend just a few light-years. These different activity levels reflect fundamental differences in their surroundings and feeding mechanisms. M87 star sits at the center of a giant elliptical galaxy that has likely grown through multiple major galaxy mergers, which have funneled vast amounts of gas to the central region. Additionally, M87 itself lies at the heart of the Virgo cluster, where it can accrete gas from the hot intracluster medium. Sagittarius A star, meanwhile, resides in a spiral galaxy with less dramatic merger history and currently has a relatively limited gas supply in its immediate vicinity. The imaging process for these two black holes presented contrasting challenges to the Event Horizon Telescope team. M87's enormous mass means that the timescale for significant changes in its appearance is relatively long. Material takes days to orbit the black hole, allowing astronomers to combine observations taken over multiple nights as if the target were static. Sagittarius A star, being much less massive, changes on timescales of minutes rather than days. Gas orbiting near its event horizon completes a full circuit in just 30 minutes, causing the black hole's appearance to change during the very observations intended to capture it. This required special techniques to account for this variability when processing the Sagittarius A star data. Another key difference is in their spin rates. While precise measurements remain challenging, evidence suggests that M87 star rotates relatively slowly compared to its maximum possible rate. Sagittarius A star, however, appears to be spinning quite rapidly, based on observations of material in its immediate vicinity. These different spin rates affect everything from the efficiency with which the black holes convert infalling mass to energy to the detailed structure of space-time surrounding them. The different masses of these black holes also mean they experience time very differently. Due to gravitational time dilation, clocks at a fixed distance from a black hole's event horizon run more slowly than distant clocks. Near Sagittarius, a star, this effect is substantial. But around the much more massive M87 star, the time dilation effect extends much farther out from the event horizon, affecting a vastly larger volume of space. Despite their differences, the images of both black holes show striking similarities that confirm fundamental predictions of Einstein's general relativity. Both appear as bright rings surrounding a central dark region or shadow. The similar appearance of these vastly different black holes demonstrates that the basic physics governing their immediate environment scales consistently across an enormous range of masses. This universality is one of the most profound insights from comparing these two objects. The same physical principles apply whether a black hole is millions or billions of times the mass of our Sun. The comparison between Sagittarius A star and M87 star serves as an invaluable check on our theoretical understanding. If our models can accurately describe both objects despite their vastly different properties, it suggests those models capture the essential physics of black holes in general. Conversely, any discrepancies between observations and predictions provide clues about where our understanding might be incomplete. For astronomers, having detailed observations of these two very different black holes is somewhat like having both a cheetah and an elephant to study when trying to understand mammals. The extreme differences highlight which features are fundamental to all objects in the class and which are variable. The similarities in their images confirm that the basic structure of a black hole's appearance, a bright ring around a dark shadow, is universal, while differences in their behavior and surroundings illustrate how black holes interact with their environments in mass-dependent ways. As observation techniques improve, astronomers plan to expand their comparative studies to include additional supermassive black holes with different masses, spin rates, and accretion states. This growing sample will provide an increasingly complete picture of how these extraordinary objects behave across the full range of cosmic environments. The insights gained from comparing Sagittarius, A star and M87 star extend beyond black hole physics to galaxy evolution more broadly. The dramatic differences in their host galaxies, one a barred spiral of moderate size, the other a giant elliptical at the center of a galaxy cluster, provide context for understanding how different galactic environments influence the growth and activity of their central black holes. This comparative approach represents one of the most powerful tools astronomers have for untangling the complex relationships between supermassive black holes and their galactic hosts. While scientists continue to study these fascinating cosmic objects from a safe distance, a question naturally arises in the human imagination. What if we could somehow visit Sagittarius, a star, up close? What would it take to travel to our galaxy's central black hole? And what would we experience if we could actually get there? This thought experiment pushes the boundaries of both physics and technology, revealing just how extraordinary black holes truly are. The journey to Sagittarius, a star, would first and foremost be an exercise in patience. At approximately 26,000 light-years from Earth, the black hole sits at an almost unimaginable distance. With our current chemical rocket technology, which can achieve speeds of around 40,000 kilometers per hour at best, such a journey would take more than 400 million years, roughly 100 times longer than humans have existed as a species. Even our most ambitious theoretical propulsion systems offer little practical hope. A nuclear pulse propulsion system, similar to the never-built Project Orion concept, might achieve speeds of around 4 to 5% of the speed of light. This would reduce the travel time to only about 500,000 years. More speculative technologies like fusion rockets or antimatter drives might push this to 10 or 20% of light speed, potentially bringing the journey down to something like 130,000 years, still far beyond any practical mission duration. The fastest spacecraft humans have ever built, Parker Solar Probe (DOT), will eventually reach speeds of about 690,000 kilometers per hour as it makes close approaches to the Sun. Even at this extraordinary speed, it would take more than 40,000 years to reach Sagittarius, a star. These sobering timescales don't even account for the enormous practical challenges of navigating the interstellar medium. The space between stars isn't truly empty, but contains diffuse gas and dust. At high speeds, collisions with even tiny particles would release enormous energy, potentially damaging or destroying a spacecraft. Shielding against these impacts, as well as the cosmic radiation permeating interstellar space, would add significant mass to any potential mission, further complicating propulsion requirements. But let's imagine we somehow overcame these challenges with some revolutionary propulsion technology that allowed us to approach significant fractions of the speed of light. As we neared the galactic center, we'd encounter an increasingly hazardous environment. The region around Sagittarius A star contains high concentrations of stars, about 10 million stars within just 1 parsec of the black hole, compared to the nearest star to our Sun being over 1 parsec away. This stellar density creates a radiation environment thousands of times more intense than near Earth, with high levels of X-rays and ultraviolet radiation that would be lethal to unshielded humans. Additionally, the galactic center contains powerful magnetic fields, dense molecular clouds, and streams of high-energy particles from previous outbursts of Sagittarius A star. Navigating this environment would require extensive shielding and precise course plotting to avoid both visible stars and invisible hazards. As our hypothetical spacecraft approached within a few light years of Sagittarius A star, the black hole's influence would become increasingly apparent. Stars would appear to move at extraordinary speeds in chaotic orbits. Light from background stars would be noticeably bent by the black hole's gravity, creating strange distortions in the visible star field. The accretion disk would become visible as a bright, hot ring of gas, emitting primarily in X-rays and other high-energy wavelengths. If we could somehow survive the journey and the environment, approaching the event horizon itself would produce even more extreme effects. The intense gravitational gradient, the difference in gravitational pull between the part of the spacecraft closest to and farthest from the black hole, would create tidal forces that would stretch any physical object along the radial direction while compressing it in perpendicular directions. For a black hole the size of Sagittarius A star, these tidal forces would become lethal for humans at a distance of roughly 6,000 kilometers from the event horizon, a process whimsically known as spaghettification because it stretches objects into long, thin shapes. Even before reaching this point, relativistic effects would become increasingly pronounced. Time dilation would cause mission clocks to tick noticeably slower compared to clocks back on Earth. Light from behind the spacecraft would be increasingly redshifted, while light from ahead would be blue-shifted. The apparent position of stars would be dramatically shifted from their actual locations due to the extreme bending of light paths. For an external observer watching this approach, our spacecraft would appear to move more and more slowly as it neared the event horizon, due to gravitational time dilation. From their perspective, we would never actually cross the horizon, instead becoming frozen in time at the boundary, our image growing increasingly redshifted and dim. However, from our perspective on the spacecraft, crossing the event horizon would not be marked by any locally detectable event. Space-time appears smooth from the perspective of the falling object. Once past the horizon, the most profound aspect of black hole physics would become apparent: the inevitability of the singularity. Inside the event horizon, space-time is warped in such a way that all future paths lead inexorably toward the central singularity. Just as we cannot avoid moving forward in time under normal circumstances, inside a black hole we cannot avoid moving toward the singularity. The crushing gravitational forces would destroy any physical object long before reaching the theoretical singularity at the center. Perhaps the most sobering aspect of this thought experiment is the one-way nature of the journey. Even if we could somehow reach Sagittarius A star and survive near its event horizon, we could never transmit our findings back to Earth once we cross the horizon. By definition, no signal can escape from within a black hole, meaning the knowledge gained from such a journey would be forever locked away from the rest of humanity. Given these insurmountable challenges, our exploration of Sagittarius A star will remain confined to remote observation for the foreseeable future. Rather than physical travel, astronomers will continue to use ever more sophisticated telescopes and computational models to study our galaxy's central black hole from a safe distance. These methods, while less romantic than imagined voyages, have already revealed extraordinary insights and will continue to deepen our understanding of these cosmic extremes without requiring us to venture into their deadly embrace. While the prospect of physically travelling to Sagittarius A star remains firmly in the realm of science fiction, astronomers have developed an extraordinary array of technological tools that allow us to study our galaxy's central black hole from the safety of Earth. These sophisticated instruments represent the culmination of decades of engineering innovation. pushing the boundaries of what humans can observe across the vast distances of space. Radio astronomy has been at the forefront of Sagittarius A* research since the black hole's initial discovery. The Very Large Array in New Mexico, consisting of 27 radio antennas arranged in a Y-shaped configuration, has been instrumental in mapping the radio emissions from the galactic center since the 1970s. Each antenna is 25 meters in diameter, and when working together, they can achieve resolution equivalent to a single dish up to 36 kilometers across. This facility has provided crucial information about the structure of the radio source associated with Sagittarius A*. For even higher resolution observations, astronomers use Very Long Baseline Interferometry, VLBI, linking radio telescopes across continents or even around the world. Before the Event Horizon Telescope, arrays like the Very Long Baseline Array, VLBA, with 10 radio antennas spread across the United States from Hawaii to the Virgin Islands, provided some of the sharpest views of the galactic center, revealing details about the size and structure of the radio emission from Sagittarius A*. At shorter wavelengths, the Atacama Large Millimeter/Submillimeter Array, ALMA, in northern Chile has revolutionized our view of Sagittarius A*. Operating at millimeter and submillimeter wavelengths, ALMA consists of 66 high-precision antennas located on the Chanantor Plateau at an altitude of 5,000 kilometers. The dry, high-altitude environment is crucial for minimizing atmospheric interference at these wavelengths. ALMA not only serves as a powerful telescope in its own right, but also played a critical role as part of the Event Horizon Telescope network. To study the high-energy radiation from Sagittarius A*, astronomers rely on X-ray observatories in space, as Earth's atmosphere blocks these wavelengths. NASA's Chandra X-ray Observatory, launched in 1999, has been particularly important for monitoring X-ray flares from Sagittarius A*. With its ability to resolve features as small as half an arcsecond, equivalent to reading a newspaper headline from half a mile away, Chandra has provided detailed images of the hot gas surrounding the black hole and tracked changes in its activity over more than 2 decades. Another space-based observatory, NuSTAR Nuclear Spectroscopic Telescope Array, launched in 2012, focuses on higher energy hard X-rays. It has detected flares from Sagittarius A* that reach temperatures of 100 million degrees Celsius, providing insights into the energetic processes occurring near the event horizon. For studying the stars orbiting Sagittarius A*, infrared observations are essential, as this wavelength can penetrate the dust clouds obscuring the galactic center in visible light. The twin 10-meter Keck telescopes on Mauna Kea in Hawaii have been crucial in this work. Equipped with adaptive optic systems that use lasers to create artificial guide stars, these telescopes can correct for atmospheric turbulence, achieving resolution close to the theoretical limit. The gravity instrument on the European Southern Observatory's Very Large Telescope Interferometer in Chile combines the light from 4 8.2-meter telescopes to achieve even more precise measurements of stellar positions, allowing astronomers to track the orbit of the star S2 during its closest approach to Sagittarius A*. The James Webb Space Telescope, launched in December 2021, represents the newest addition to the arsenal of tools for studying Sagittarius A*. Its unparalleled sensitivity in the infrared wavelengths and freedom from atmospheric interference will allow it to detect fainter stars and gas structures near the black hole than ever before, potentially revealing new details about the feeding processes and environment of Sagittarius A*. Behind all these observational tools lies an equally impressive array of computational resources. The raw data collected by these telescopes is often not immediately usable for scientific analysis. Complex algorithms running on supercomputers are needed to process the signals, remove interference, calibrate measurements, and transform the data into meaningful images and spectra. For instance, the Event Horizon Telescope data processing required computing facilities around the world working for months to synthesize the raw observations into the final historic image. Theoretical tools complement these observational capabilities. Sophisticated computer simulations of black hole accretion flows, run on some of the world's most powerful supercomputers, allow astronomers to model what they expect to see under various conditions. These simulations incorporate general relativity, magnetohydrodynamics, and radiative transfer physics to predict how material behaves in the extreme environment near Sagittarius A star and what signals should reach our telescopes. By comparing these simulations with actual observations, scientists can refine their understanding of the physical processes at work. Time synchronization technology represents another crucial tool in the study of Sagittarius A star. To combine signals from telescopes spread across the globe, astronomers need to know precisely when each observation was made. The Event Horizon Telescope relies on hydrogen mesa atomic clocks at each observatory site, capable of maintaining time to within a fraction of a trillionth of a second. Without this extreme precision timing, it would be impossible to correlate the data from different locations into a coherent whole. The development of these sophisticated tools reflects the extraordinary challenges involved in studying an object 26,000 light-years away that cannot be directly seen. Each new generation of instruments has pushed technical boundaries, requiring innovations in electronics, materials science, signal processing, and computing. The study of Sagittarius A star has driven technological advancement, with many of the techniques developed for black hole astronomy finding applications in other scientific fields and eventually in consumer technology. Future technologies promise to reveal even more about Sagittarius A star. Next-generation, very long baseline interferometry networks will include more telescopes with greater sensitivity, potentially allowing for video-like imaging of the dynamic environment around the black hole. Space-based interferometers could eventually achieve even higher resolution by escaping the limitations of Earth's atmosphere and geography. Gravitational wave observatories may someday detect ripples in space-time caused by objects falling into Sagittarius A star, providing an entirely new channel of information about our galaxy's central black hole. Despite their incredible sophistication, these technological tools all face the same fundamental challenge: capturing an image of something that, by its very nature, cannot be directly seen. The journey from theoretical concept to actual image of Sagittarius A star represents one of the most demanding photographic challenges ever undertaken, requiring scientists to overcome obstacles that once seemed insurmountable. The fundamental difficulty in photographing a black hole arises from its defining characteristic: nothing, including light, can escape from within the event horizon. This means that black holes themselves emit no radiation that we can detect. What astronomers actually observe is not the black hole itself, but the effects it has on its surroundings. The material heated to extreme temperatures as it falls in, the shadow cast against background light, and the bending of light paths by the black hole's gravity. The first challenge in imaging Sagittarius A star is its tremendous distance. At 26,000 light-years away, the black hole's event horizon spans an angle of just about 20 microarc seconds on the sky, roughly equivalent to seeing an orange on the moon from Earth. Resolving such a tiny feature requires a telescope with an effective diameter comparable to the size of our planet, which is physically impossible to build as a single structure. The solution came through interferometry, combining observations from multiple telescopes to achieve resolution equivalent to a much larger instrument. But even with this technique, imaging Sagittarius A star pushed far beyond what had previously been achieved. The Event Horizon Telescope needed to synchronize observations with atomic clock precision and maintain stability at sub-millimeter wavelengths, where atmospheric turbulence and water vapor cause severe distortion. Another major challenge comes from the material surrounding Sagittarius A star, which changes rapidly, while the black hole itself remains relatively stable. The hot gas in its vicinity can transform substantially in just minutes. This creates a significant problem by the time a telescope array observes different parts of the object. The subject itself has changed. It's like trying to photograph a fast-moving child who refuses to sit still, but with the added complication that different parts of the image are captured at different times. The Event Horizon Telescope team developed sophisticated algorithms to account for this variability, essentially creating composite images that represent the average appearance of Sagittarius A star during the observation period. This required not just collecting data but developing entirely new mathematical frameworks for interpreting rapidly changing astronomical sources. Interstellar dust presents yet another obstacle. The 26,000 light-years between Earth and Sagittarius, a star are filled with dust clouds that completely block visible light from the galactic centre. This forced astronomers to observe at radio wavelengths, which can penetrate the dust, but come with their own challenges. Radio observations typically provide much lower resolution than optical ones, making the already difficult task of resolving the black hole's small apparent size even harder. The solution involved observing at the shortest radio wavelengths possible, around 1.3 millimeters, which provides the best combination of dust penetration and resolution. Even at this wavelength, the dust and gas along the line of sight scatter the radio waves, blurring the image in a process similar to how fog diffuses light from a distant street lamp. Advanced algorithms were needed to mathematically undo this scattering effect and recover a sharper image. Weather added yet another layer of difficulty. For the Event Horizon Telescope to work, clear conditions were needed simultaneously at multiple locations around the world, from Hawaii and Arizona to Chile, Mexico, Spain, and Antarctica. This requirement severely limited the possible observation windows to just a few days per year when weather patterns might cooperate across these diverse regions. Data management presented its own massive challenge. The observations generated unprecedented volumes of data, several petabytes across the entire array. This was too much to transmit over the internet, especially from remote locations like the South Pole Telescope in Antarctica. Instead, physical hard drives had to be transported by airplane after the observation season ended, resulting in months of delay before all the data could even be assembled in one place for processing. Once collected, turning this mountain of raw data into an image required solving an enormously complex mathematical problem. The observations didn't directly produce an image, but rather measured patterns of radio wave interference. Converting these patterns into a picture involved a process called image reconstruction, which is fundamentally ambiguous. Multiple possible images could potentially be consistent with the same data. To address this ambiguity, the team used various image reconstruction algorithms and looked for features that appeared consistently across different methods. They also compared the results with simulations based on general relativity to ensure the final image was physically plausible. The famous ring-like structure around the dark central shadow emerged as a robust feature across all these approaches, giving scientists confidence that they were seeing a real structure rather than an artifact of the processing. Perhaps the most remarkable aspect of this achievement is that it required pushing multiple technologies to their absolute limits simultaneously. Any single aspect, the timing precision, the data processing, the atmospheric correction, the global coordination, would have represented a significant scientific accomplishment on its own. Combining all these advances to produce the first image of Sagittarius A star stands as one of the most complex technical achievements in the history of astronomy. The resulting image, while seemingly simple, a blurry, ring-like structure with a dark centre, represents the culmination of over a century of theoretical work on black holes, decades of technological development, and years of dedicated effort by hundreds of scientists around the world. This apparently straightforward picture contains within it confirmation of Einstein's century-old predictions about gravity, evidence for the existence of event horizons, and a direct view of the environment around an object so extreme that it defies our everyday understanding of reality. Behind the impressive technological feat of capturing Sagittarius, a star's image, lies an even greater mystery. What exactly is happening at the very centre of the black hole? While the Event Horizon Telescope has shown us the environment immediately surrounding Sagittarius A star, the heart of the black hole itself, what physicists call the singularity, remains hidden from direct observation, enshrouded by the event horizon. This central singularity represents one of the most profound puzzles in modern physics, a place where our current understanding of the universe breaks down completely. According to Einstein's general relativity, the matter that forms Sagittarius A star has collapsed to an infinitely dense point at the centre, creating a singularity where space-time curvature becomes infinite. At this mathematical point, the equations that describe gravity simply stop working. They produce infinities, which physicists interpret as a sign that the theory itself is reaching its limits of applicability. This doesn't mean that general relativity is wrong. Rather, it tells us where the theory needs to be superseded by something more comprehensive. What makes the singularity particularly fascinating is that it represents a fundamental limit to our knowledge. The event horizon acts as a cosmic sensor, preventing any information from the singularity from reaching outside observers. This concept, proposed by Roger Penrose and known as the cosmic censorship hypothesis, suggests that nature protects us from the bizarre physics at singularities by always hiding them behind event horizons. While we can mathematically describe what should happen at the singularity, we cannot directly test these predictions through observation. The singularity at Sagittarius, a star's centre, contains, in some sense, the compressed remains of everything that has fallen into the black hole throughout its long history. Millions of stars, vast clouds of gas, and perhaps smaller black holes have all been drawn in over billions of years, their matter adding to Sagittarius A's mass, but their distinct physical characteristics erased in the process. According to classical general relativity, all this material is crushed to a dimensionless point, with no volume but enormous mass. Most physicists believe this classical picture cannot be the full story. The infinite densities and curvatures predicted at the singularity likely indicate where quantum effects become crucial for understanding gravity. In regions of such extreme density, space and time themselves may dissolve into something more fundamental, perhaps a quantum foam of fluctuating space-time, or strings of energy vibrating in multiple dimensions, or something else entirely that current theories haven't yet conceived. Various approaches to quantum gravity, the still developing theory that would unite general relativity with quantum mechanics, offer different perspectives on what might replace the singularity. String theory suggests that instead of a point-like singularity, there might be a small but finite region where strings, one-dimensional vibrating filaments of energy, exist in a highly excited state. Loop quantum gravity, another contender, proposes that space-time itself has a granular structure at the smallest scales, preventing infinite compression. Some theoretical models suggest that the interior of a black hole might contain not a singularity but a wormhole, a theoretical tunnel through space-time that could potentially connect to another region of our universe, or even another universe entirely. While mainstream physics remains skeptical of such possibilities, they highlight how little we truly know about what happens in these extreme environments. The mystery deepens when we consider how information is processed at the singularity. Everything that falls into Sagittarius, a star, carries information, the specific arrangement of particles, their quantum states, their relationships with other particles. According to quantum mechanics, this information should never be completely destroyed. Yet the singularity appears to erase all distinctions between different types of infalling matter. This tension underlies the black hole information paradox, one of the most profound conundrums in theoretical physics. Hawking radiation, the theoretical process by which black holes slowly evaporate over time, further complicates our understanding of the singularity. If black holes eventually evaporate completely, what happens to the singularity when it's gone? Does the information somehow escape during the evaporation process? For Sagittarius, a star, with its enormous mass. Such evaporation would take an unimaginably long time, roughly 10 to the power of 87 years, far longer than the current age of the universe, making this question purely theoretical for our particular black hole. Recent theoretical work has begun to suggest that black hole singularities might be less point-like and more extended than classical general relativity indicates. Some calculations hint at a structure called a fuzzball, where the singularity is replaced by a ball of quantum string, states that has a size comparable to the event horizon itself. Others propose that quantum effects might create an effective repulsive force that prevents complete collapse, resulting in a regular black hole with no true singularity at all. What makes these questions more than mere academic curiosities is their connection to the fundamental nature of space, time, and information. The singularity at Sagittarius, a star's center, challenges our deepest theories about reality. If we could somehow understand what happens there, we might gain insight into questions that have puzzled physicists and philosophers alike. Is information ever truly lost? Is space-time fundamental or emergent from something deeper? What happens when the known laws of physics collide with each other? For now, the singularity remains shrouded behind the event horizon, invisible to our telescopes and possibly fundamentally unknowable through direct observation. Yet its presence influences everything around it, shaping the dynamics of gas, dust, and stars in the galactic center, and even affecting the structure of spacetime that we can observe. The singularity serves as a reminder of how much we still don't understand about the universe, even as we celebrate the remarkable achievement of photographing a black hole's shadow. This profound mystery at Sagittarius, a star's core, sits at the center of a remarkably dynamic and extreme environment, while the singularity itself remains hidden. The region surrounding our galaxy's central black hole represents one of the most extraordinary laboratories for cosmic physics in the Milky Way. Here, in the central few light years around Sagittarius, a star, astronomers find a dazzling array of objects and phenomena that exist nowhere else in our galactic neighborhood. The most immediately striking feature of this environment is its stellar density. Within just 1 parsec, about 3.26 light-years, of Sagittarius, a star, astronomers have identified thousands of stars, packed together at densities millions of times greater than in our solar neighborhood. This cluster, known as the nuclear star cluster, contains a remarkable diversity of stellar objects, from relatively normal stars similar to our Sun to exotic varieties rarely seen elsewhere. Among the most fascinating inhabitants of this crowded neighborhood are the S-stars, a group of young, massive blue stars that orbit extremely close to Sagittarius A star. Their very existence is puzzling, as the intense tidal forces near the black hole should theoretically prevent the gas clouds from which stars form from condensing. Astronomers have proposed several explanations. Perhaps these stars formed farther out and migrated inward, or maybe they formed from the collision and merger of smaller stars, or possibly they were born in the remnants of a massive disk of gas around the black hole. Another unusual population found in this region consists of G-objects, mysterious bodies that appear to have properties of both stars and gas clouds. These objects follow elliptical orbits, bringing them dangerously close to Sagittarius A star, where tidal forces stretch them dramatically before they swing back out to safer distances. Some astronomers believe these could be binary star systems embedded within dust clouds, or perhaps stars in the process of merging due to the black hole's gravitational influence. Beyond stars, the central region contains vast amounts of gas organized into complex structures. A disk-like feature called the circumnuclear disk orbits about 2 to 7 parsecs from the black hole, containing approximately 10,000 solar masses of molecular gas and dust. This disk appears clumpy rather than smooth, with dense regions that might eventually collapse to form new stars. Streamers of gas occasionally break off from this disk and spiral inward towards Sagittarius A star, providing fuel for future accretion events. Closer to the black hole, at about 1/10 of a parsec, lies the mini-spiral, a structure of ionized gas heated to thousands of degrees by radiation from nearby stars. This feature appears to be flowing inward towards Sagittarius A star at speeds of hundreds of kilometers per second, potentially setting the stage for increased black hole activity in the coming thousands of years. The environment around Sagittarius A star is also permeated by powerful magnetic fields. Radio observations have revealed massive magnetic filaments, some extending tens of parsecs in length, oriented perpendicular to the galactic plane. These structures appear to channel high-energy particles, creating cosmic highways through the galactic center region. The origin of these magnetic filaments remains debated, but they may be connected to past outbursts from Sagittarius A star or to the complex interactions between stellar winds, supernova remnants, and the larger galactic magnetic field. One of the most dramatic features in this cosmic laboratory is the presence of occasional X-ray flares emanating from very close to Sagittarius A star. These flares, detected by the Chandra and New Star X-ray observatories, can make the black hole brighten by factors of tens to hundreds over its baseline emission in a matter of minutes, before fading back to normal within an hour. These events likely represent magnetic reconnection events in the innermost accretion flow, similar to solar flares but vastly more powerful, releasing enormous amounts of energy as magnetic field lines break and reconnect in new configurations. The radiation environment around Sagittarius A star is extreme by any terrestrial standard. The combined effect of so many stars packed into a small volume creates a bath of ultraviolet light hundreds of times more intense than in our solar neighborhood. Added to this are X-rays from the hot gas near the black hole and from numerous stellar remnants, along with cosmic rays accelerated by magnetic fields and shockwaves. This harsh radiation environment has implications for the chemistry of gas clouds in the region, potentially driving exotic reactions that would be rare elsewhere in the galaxy. Remarkably, despite these extreme conditions, the central parsecs around Sagittarius A star show evidence of ongoing star formation. Young stellar objects and small star clusters have been detected, suggesting that the hostile environment doesn't completely prevent new stars from being born. This challenges conventional models of star formation and demonstrates nature's tendency to find pathways for creation even in the most forbidding circumstances. The age distribution of stars near Sagittarius A star tells a complex story of the region's history. While many stars appear quite young, just millions of years old, others are ancient, having orbited the black hole for billions of years. This mixture suggests that star formation near Sagittarius A star has happened in distinct episodes rather than continuously, perhaps triggered by specific events like the infall of large gas clouds or disturbances from passing satellite galaxies. This entire cosmic laboratory moves with surprising coordination. The nuclear star cluster rotates as a unit around Sagittarius A star, while also having considerable random motion among its stellar members. This complex dynamical state reflects both the overwhelming influence of the black hole's gravity and the cumulative effects of countless gravitational interactions among the stars themselves, a process astronomers call two-body relaxation that gradually redistributes energy throughout the cluster. What makes this environment so valuable to astronomers is that it allows them to study extreme physics under conditions impossible to replicate on Earth. The intense gravity, powerful magnetic fields, high radiation densities, and enormous energy transfers provide natural experiments in how matter behaves under conditions far beyond anything in our everyday experience or laboratory capabilities. Observing how gas clouds fragment or stars evolve in this environment helps scientists refine their theories of these processes under extreme conditions. The presence of so many stars following different orbits around Sagittarius A star provides multiple probes of the gravitational field. allowing for increasingly precise tests of general relativity. The occasional flares give glimpses of plasma physics in regimes of temperature and density otherwise inaccessible to direct study. As observational capabilities improve, this cosmic laboratory will likely yield even more insights. Future telescopes with higher resolution and sensitivity will resolve finer details in the gas structures and detect fainter stars even closer to Sagittarius A star. Multi-wavelength campaigns coordinating observations across the electromagnetic spectrum will provide more complete pictures of the complex processes unfolding in this remarkable environment, where the extreme becomes commonplace and the impossible becomes routine. Within the remarkable cosmic laboratory surrounding Sagittarius, a star, astronomers are pursuing another intriguing mystery: the potential existence of intermediate mass black holes orbiting our galaxy's central supermassive black hole. These elusive objects would fill a crucial gap in our understanding of black hole evolution, representing a missing link between stellar mass black holes, those with roughly 5 to 100 solar masses, and supermassive giants like Sagittarius A star, millions to billions of solar masses. Intermediate mass black holes, or IMBHS, would fall in the range of hundreds to tens of thousands of solar masses, substantially larger than what can form from a single collapsing star, but much smaller than the behemoths at galactic centers. Their existence has been theorized for decades, but conclusive evidence has remained frustratingly difficult to obtain anywhere in the universe. The region around Sagittarius A star offers one of the most promising hunting grounds for these cosmic middleweights. Several lines of evidence suggest that IMBHS might be lurking in the galactic center. Computer simulations of galactic evolution indicate that when smaller galaxies are absorbed by larger ones, a common occurrence in cosmic history, the smaller galaxies' central black holes should eventually make their way to the core of the merged galaxy. Given that the Milky Way has cannibalized numerous dwarf galaxies throughout its lifetime, it should theoretically have accumulated several intermediate-sized black holes that are now orbiting somewhere in the central region. Detecting these objects presents enormous challenges. However, they are too small to image directly with current technology, and they don't necessarily produce obvious emission signatures if they're not actively feeding on surrounding material. Instead, astronomers must look for subtle gravitational effects, the ways these invisible objects influence visible stars and gas clouds. One approach involves searching for stars moving at unusually high velocities or following strange trajectories that could indicate they've been gravitationally kicked by an encounter with an unseen massive object. Astronomers have identified several hypervelocity stars racing away from the galactic center at speeds sufficient to escape the Milky Way entirely. While Sagittarius A star itself could be responsible for some of these stellar slingshots, the trajectories of others suggest encounters with something less massive, potentially intermediate black holes. Another detection method focuses on gravitational microlensing, brief brightening events that occur when a massive object passes in front of a background star, its gravity bending and focusing the star's light. Extended monitoring of thousands of stars near the galactic center can potentially reveal such events, providing evidence for otherwise invisible IMBHS. Radio and X-ray observations offer additional avenues for detection. If an intermediate mass black hole happens to be consuming matter, it should produce distinctive emission patterns different from both stellar mass black holes and Sagittarius A star itself. Several candidate objects have been identified, including a particularly interesting X-ray source designated 3XMMJ215022, 4-055108, which appears to have a mass of about 50,000 solar masses. Perhaps the most tantalizing evidence comes from irregularities in the distribution of stars very close to Sagittarius A star. Some clusters and streams of stars show patterns that could be explained by the gravitational influence of an IMBH with roughly 1,000 solar masses orbiting just a few light-years from the central supermassive black hole. If confirmed, The presence of these intermediate black holes would have profound implications for our understanding of both Sagittarius A star and black hole evolution generally. First, they would represent important building blocks in the growth of supermassive black holes. Many theorists believe that supermassive black holes like Sagittarius A star grew at least partially through mergers with smaller black holes rather than solely through accreting gas. Finding IMBHS in the process of spiraling towards Sagittarius A star would provide direct evidence for this growth mechanism. Additionally, these objects would eventually merge with Sagittarius A star, an event that would release enormous energy in the form of gravitational waves. While current gravitational wave detectors like LIGO and Virgo aren't sensitive to the low frequencies produced by such mergers, future observatories like the space-based LISA, Laser Interferometer Space Antenna, could potentially detect them, offering an entirely new way to study our galaxy's central black hole. The search for intermediate mass black holes around Sagittarius A star also connects to broader questions about dark matter. Some theories propose that the galactic center might contain numerous smaller black holes that collectively contribute to the concentration of mass in that region. These could even be primordial black holes, hypothetical objects formed in the early universe that some researchers have suggested might constitute a portion of dark matter. Most excitingly, if astronomers do conclusively identify intermediate mass black holes orbiting Sagittarius A star, these objects would provide unique opportunities to test general relativity in new regimes. The dance between two black holes of different masses would create distinctive gravitational effects that could be measured through their influence on surrounding stars and gas, potentially revealing subtle departures from Einstein's predictions if any exist. The galactic center likely contains numerous black holes of various masses, forming a sort of black hole cemetery where these objects have accumulated over billions of years of galactic evolution. Current estimates suggest that thousands of stellar mass black holes might reside within the central parsec around Sagittarius A star, along with a smaller number of intermediate mass objects. As observational techniques improve, astronomers hope to construct a more complete census of these dark denizens, filling in our understanding of how black holes of all sizes coexist and interact in the crowded core of our galaxy. The ongoing search for intermediate mass black holes around Sagittarius A star exemplifies how our understanding of the universe continually evolves, with each discovery raising new questions and opening new frontiers of exploration. This pattern of expanding knowledge has characterized the entire history of our study of Sagittarius A star, a journey that has fundamentally transformed our understanding of black holes and the universe at large. When astronomers first detected unusual radio emissions from the direction of the galactic center in the 1930s, few could have imagined they were detecting the first hints of one of the most extreme objects in physics. The very concept of black holes was largely considered a mathematical curiosity rather than a real astrophysical phenomenon. Even after Carl Jansky's pioneering detection of radio waves from the galactic center, decades passed before technology advanced sufficiently to begin resolving the structure of what we now call Sagittarius A star. The historical progression of our understanding illustrates one of the most remarkable scientific journeys of the modern era. In the 1950s and 60s, improved radio telescopes began to reveal structure in the galactic center emission, but the nature of these sources remained mysterious. When astronomers Bruce Balick and Robert Brown detected the compact radio source they designated as Sagittarius A star in 1974, they had found what would eventually be recognized as our galaxy's central black hole, though confirming this would take decades more work. The transformation in our understanding accelerated in the 1990s with the dawn of infrared observations that could penetrate the dust obscuring the galactic center. When Andrea Ghez at UCLA and Reinhard Genzel in Germany began tracking individual stars orbiting an invisible object at the precise location of Sagittarius A star, they were laying the groundwork for one of astronomy's most significant discoveries. Their meticulous observations, continued over decades, provided the first definitive evidence that supermassive black holes, objects that had long existed primarily in theory and speculation, were real. This confirmation represented a profound shift in our understanding of the universe. Black holes moved from theoretical mathematical solutions of Einstein's equations to confirmed astrophysical objects that could be observed and studied. The 2020 Nobel Prize in Physics, awarded to Ghez and Genzel, recognized not just their technical achievement, but the paradigm-shifting nature of their discovery. Their work on Sagittarius A star proved that supermassive black holes aren't exotic rarities but standard features of galaxy centers throughout the cosmos. The study of Sagittarius A star has also served as one of the most stringent tests of Einstein's general relativity. The theory, published in 1915, makes specific predictions about how objects should behave in strong gravitational fields. For most of the century following Einstein's work, astronomers could only test these predictions in relatively weak gravitational environments like our solar system. Sagittarius A star changed that by providing a natural laboratory where gravity reaches extremes previously inaccessible to observation. The precession of the star S2's orbit around Sagittarius A star, the gravitational redshifting of its light during close approach, and ultimately the shape and size of the shadow seen in the Event Horizon Telescope image all matched the predictions of general relativity with remarkable precision. Each of these confirmations further cemented Einstein's century-old theory as one of the most successful in scientific history. Correctly describing phenomena the theory's creator could never have hoped to observe directly. Beyond validating existing theories, the study of Sagittarius A star has transformed our understanding of how galaxies form and evolve. Before detailed observations of our galactic center, astronomers didn't fully appreciate the intimate connection between supermassive black holes and their host galaxies. The discovery of the tight correlation between black hole mass and galactic properties revealed that these objects aren't merely passive residents, but active participants in galactic evolution, influencing star formation and the distribution of matter throughout their host galaxies. The technological advances driven by the desire to study Sagittarius A star have revolutionized astronomy more broadly. Adaptive optics systems developed to peer through Earth's atmosphere to the galactic center now serve as standard technology on major telescopes worldwide, enhancing observations of countless other astronomical objects. Radio interferometry techniques refined for studying Sagittarius A star have been applied across radio astronomy, dramatically increasing the resolution available for studying distant cosmic sources. Perhaps most profoundly, Sagittarius A star helped bridge theoretical physics and observational astronomy, two disciplines that had sometimes developed along separate tracks. The abstract mathematical descriptions of black hole physics suddenly had a concrete object against which they could be tested. Theorists' predictions about event horizons, ergospheres, and gravitational lensing could be checked against actual observations, grounding theoretical speculation in empirical reality. The study of Sagittarius A star also exemplifies the inherently collaborative and international nature of modern science. The decades-long journey from detection to imaging has involved thousands of researchers across dozens of countries, working with instruments on every continent and in space. This collaboration transcended political boundaries, uniting scientists in the common pursuit of understanding one of the most extreme objects in our cosmic neighborhood. The evolution in our understanding of Sagittarius A star mirrors the broader pattern of scientific progress, moving from detection of an unexplained phenomenon to characterization, to theoretical modeling, and finally to comprehensive understanding validated by multiple lines of evidence. At each stage, new technologies enabled observations that would have seemed impossible a generation earlier, while theoretical insights guided observers toward the most revealing measurements to make. This journey has been marked by both incremental advances and dramatic breakthroughs. Years of painstaking observations of stellar orbits gradually built the case that something extraordinarily massive yet compact lurked at the galactic center. The Event Horizon telescope image then provided a dramatic visual confirmation that captured the public imagination while validating decades of prior scientific work. Looking back on this historical progression reveals something profound about human curiosity and ingenuity. A century ago, Einstein's equations suggested that black holes could theoretically exist, but few scientists believed they would ever be more than mathematical curiosities. Today, not only do we know that Sagittarius A star exists, but we have photographed its shadow, tracked stars orbiting it, measured the space-time distortions it creates, and built sophisticated models of the physics at its event horizon. This transformation in our understanding stands as one of science's great success stories, a journey from ignorance to knowledge driven by the combination of technological innovation, theoretical insight, and persistent observation. The story of Sagittarius A star demonstrates how science at its best can gradually unveil even the most extreme and distant phenomena, bringing them within the realm of human understanding. What began as unexplained radio static detected by Bell Labs engineer Carl Jansky has revealed itself as one of the most extraordinary objects in our galaxy, forever changing our conception of the universe and our place within it. The historical journey of our understanding of Sagittarius A star not only reveals how far we've come, but also invites us to look forward, to consider the future of our galaxy's central black hole across cosmic timescales that stretch far beyond human experience. While we've observed Sagittarius A star for mere decades, this cosmic behemoth has existed for billions of years and will continue to shape our galaxy's fate for countless eons to come. In the relatively near astronomical future, the next few tens of thousands of years, Sagittarius A star is likely to experience increased feeding activity. Astronomers have identified several gas clouds on trajectories that will bring them perilously close to the black hole. The most famous of these, G2 Dot, survived its closest approach in 2014 with less disruption than expected, but future encounters may prove more dramatic. The compact object G1 will make its closest approach in the coming decades, potentially providing material for accretion. Additionally, the substantial gas reservoirs in the circumnuclear disk that orbits a few light-years from Sagittarius A star will gradually feed material inward, leading to periodic increases in activity. Over slightly longer timescales of millions of years, Sagittarius A star will continue its complex gravitational dance with the stars of the nuclear cluster. Computer simulations suggest that every 50,000 years or so, a star will be captured into a highly elliptical orbit that brings it close enough to the black hole to be partially torn apart by tidal forces. These tidal disruption events would cause bright flares lasting months to years as the stellar material heats up while spiraling into the black hole. Over millions of years, thousands of stars will meet this fate, each contributing modestly to Sagittarius A star's growth. The most dramatic change in Sagittarius A's future will begin in about 4.5 billion years, when our Milky Way galaxy begins to collide with the neighbouring Andromeda galaxy. This slow-motion cosmic crash, which will unfold over hundreds of millions of years, will fundamentally reshape both galaxies. As the two spiral galaxies pass through each other and eventually merge, enormous amounts of gas will be compressed and funneled toward the central regions, likely triggering intense star formation and substantially increased accretion onto both Sagittarius A star and Andromeda's central black hole, known as M31 star. This merger will also bring the two supermassive black holes into the same galaxy, beginning a complex orbital relationship that will shape the core of the newly formed galaxy, sometimes called Milkomeda. Initially, the two black holes will orbit each other at distances of thousands of light-years. Gradually, through a process called dynamical friction, essentially the gravitational drag created as they move through the dense star field, they will lose energy and spiral closer together. When the two black holes get within a few light-years of each other, they will form a binary system, orbiting around their common center of mass. Stars and gas caught in this binary's gravitational field will be flung outward in a process known as gravitational slingshot, effectively clearing out the central region of the merged galaxy. This ejection of stars paradoxically causes the black hole binary to lose more energy, bringing them even closer together. The final stages of the merger will be spectacular. When the black holes reach distances of just a few times their combined event horizon size, they will begin emitting copious amounts of gravitational waves, ripples in space-time that carry away the final orbital energy. In the last few minutes of the merger, these gravitational waves will become extraordinarily powerful, briefly outshining the entire electromagnetic output of the visible universe. Though this energy will be undetectable except through specialized gravitational wave observatories, the result will be a new, more massive black hole with a combined mass of roughly 10 billion solar masses. Sagittarius A's 4 million plus M31's roughly 150 million, plus any additional mass accumulated during the galaxy merger. This new black hole will likely undergo a period of intense activity as it adjusts to its new state, potentially becoming bright enough to qualify as a quasar for a relatively brief period. Beyond this merger, over timescales of tens to hundreds of billions of years, the universe will continue to expand and evolve. Star formation will gradually diminish as the available gas is depleted, and the merged galaxy will transition from a vibrant spiral to a quiescent elliptical. During this period, Sagittarius A star, or rather dot, the larger black hole it will have become after merging with M31, will continue to grow slowly by consuming the occasional star and gas cloud, as well as by merging with smaller black holes from satellite galaxies. As we look even further ahead, to truly cosmic timescales, even more profound changes await. In about 100 trillion years, star formation will cease entirely in our local group of galaxies. After that, existing stars will gradually burn out, leaving behind white dwarfs, neutron stars, and stellar mass black holes. Over unimaginably long periods, quadrillions of years, even these stellar remnants will either fall into the central supermassive black hole or be ejected from the galaxy through gravitational encounters. Eventually, after timescales so vast they dwarf the current age of the universe. Quantum effects predicted by Stephen Hawking suggest that the black hole itself will begin to lose mass through Hawking radiation. For a black hole the size of the merged Sagittarius A star and M31 star, this evaporation would take roughly 10 to the power of 100 years, a time span so enormous that it exceeds our ability to conceptualize it in human terms. During this evaporation process, the black hole would gradually lose mass, accelerating as it shrinks and becomes hotter. In its final moments, the black hole would release a burst of high-energy radiation, returning the last of its enormous mass energy to the universe. This final evaporation represents the ultimate fate of Sagittarius A star, the transition from cosmic behemoth back to energy, completing a cycle that began with the early formation of our galaxy more than 13 billion years ago. Of course, these far future predictions rest on our current understanding of physics, which may well be incomplete. New discoveries about dark energy, dark matter, or quantum gravity could significantly alter these predictions. What seems certain is that Sagittarius A star, whether as an individual object or merged with other black holes, will remain a central player in our galaxy's evolution far longer than most other astronomical structures, outlasting stars, planets, and perhaps even protons themselves. The future of Sagittarius. A star serves as a reminder of the immense timescales over which cosmic evolution unfolds, a perspective that dramatically reframes our understanding of existence and our place in the universe. This sense of cosmic perspective represents just one of the many ways that Sagittarius A star and other black holes have influenced our thinking about fundamental questions of space, time, and reality itself, beyond their astronomical significance. Black holes like Sagittarius A star have profound implications for our understanding of physics and the nature of reality. These objects push our comprehension of space, time, and physical law to their absolute limits, challenging us to reconsider assumptions that seem self-evident in our everyday experience. Perhaps the most fundamental shift in thinking that Sagittarius A star represents is the realization that space and time aren't fixed, immutable backdrops to cosmic events, but are themselves dynamic and malleable. The extreme gravity near Sagittarius A star warps space-time so severely that our intuitive notions of before and after, or here and there, break down. Near the event horizon, space and time become so thoroughly intertwined that they lose their distinct identities, merging into a unified space-time that flows like a river, carrying everything inexorably inward. This realization, though predicted mathematically by Einstein's equations, became tangible through the study of objects like Sagittarius A star. When astronomers measured the precession of S2's orbit or detected the gravitational redshift of light emitted near the black hole, they weren't just confirming abstract mathematical predictions, they were directly observing the malleability of space-time itself. The fact that space and time can be stretched, compressed, and twisted is no longer merely theoretical, but empirically verified through observations of our galaxy's central black hole. The event horizon of Sagittarius. A star represents another profound conceptual boundary, a place where causality itself takes on new meaning. Beyond this boundary, the future points inexorably toward the singularity, eliminating possibilities that we take for granted in normal experience. This absolute causal structure challenges our intuitive notions of free will and possibility, suggesting that certain fundamental aspects of reality depend on where you are in space-time. Equally significant is how black holes have forced us to reconsider information and its relationship to physical reality. The black hole information paradox, the apparent conflict between quantum mechanics' requirement that information be preserved and general relativity's suggestion that information is lost inside black holes, has driven theoretical physics into new territory. Proposed resolutions involving holographic principles suggest that our three-dimensional reality might be encoded on two-dimensional boundaries, a concept so revolutionary that it reimagines the fundamental nature of space itself. Sagittarius A star and objects like it have also transformed our understanding of energy and how it can be converted and stored. The accretion disks and jets associated with black holes represent the most efficient energy conversion processes known in the universe, turning gravitational potential energy into radiation with efficiencies that can approach 30%, far exceeding the nuclear fusion in stars, which converts less than 1% of rest mass to energy. This has implications not just for astrophysics, but for our fundamental understanding of how energy and matter interrelate. The recent imaging of Sagittarius A star's shadow has added another dimension to these implications by providing visual confirmation of what had previously been understood primarily through mathematics and indirect evidence. The simple, almost mundane appearance of the black hole's image belies the extraordinary physics it represents. That familiar-looking ring of light confirms predictions made purely through mathematical reasoning, demonstrating the power of human intellect to comprehend reality beyond direct experience. This connection between abstract mathematics and physical reality is one of the most profound implications of black hole research. The equations that describe Sagittarius A star were developed long before we had the technology to observe it directly, yet they predicted its properties with remarkable accuracy. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner described it, suggests a deep connection between mathematical structures and physical reality that continues to puzzle and intrigue scientists and philosophers alike. Sagittarius A star also serves as a potent reminder of the limits of knowledge. Despite all we've learned, the interior of the black hole remains inaccessible to direct observation. The event horizon represents not just a physical boundary, but an epistemological one, a limit to what can be empirically known through observation. This has led some physicists to reconsider what scientific knowledge means when dealing with regions of the universe that cannot, even in principle, be directly observed, beyond formal scientific understanding. Black holes like Sagittarius A star have permeated cultural consciousness, influencing how millions of people conceptualize the universe. From science fiction to popular science, black holes have become powerful symbols of the extreme, the unknown, and the limits of comprehension. The image of Sagittarius A star's shadow has already become iconic, joining other astronomical images like the pale blue dot of Earth or the pillars of creation in shaping humanity's collective cosmic perspective. This cultural impact shouldn't be underestimated. By providing concrete examples of how reality can differ from everyday experience, black holes have helped expand the imaginative capacity of the general public, making abstract concepts like curved space-time or event horizons part of common knowledge. When people view the image of Sagittarius A star, they're not just seeing an astronomical object, they're engaging with fundamental concepts about the nature of reality that were once accessible only to specialists. The study of Sagittarius A star also highlights the provisional nature of scientific knowledge. Each advance in our understanding has revealed new questions and challenges, from the initial puzzle of the radio source's nature to current debates about the information paradox. This ongoing evolution of knowledge serves as a reminder that science is not a body of final truths, but a process of progressive approximation, constantly refining and sometimes revolutionizing our understanding of reality. Perhaps most significantly, Sagittarius A star offers a cosmic perspective that contextualizes human existence. The black hole has existed for billions of years and will continue to exist for trillions more, operating on timescales that make human history seem vanishingly brief. The processes occurring near its event horizon involve energies and forces far beyond human scale. Yet through observation, mathematics, and theory, humans have managed to comprehend this object despite its remoteness in both space and conceptual familiarity. This achievement, understanding something so far beyond ordinary experience, speaks to the remarkable capacity of the human mind to transcend its immediate circumstances. Through science, we've extended our comprehension far beyond the narrow slice of reality our evolutionary history prepared us to perceive directly. The fact that we can understand objects like Sagittarius A star at all suggests that our cognitive capabilities, though evolved for entirely different purposes, somehow provide access to aspects of reality far removed from everyday human experience. As our knowledge of Sagittarius A star continues to grow, these implications will undoubtedly evolve and deepen. Each new observation and theoretical advance not only enhances our understanding of this specific astronomical object, but also contributes to our broader comprehension of the universe and our place within it. The 4 million solar mass black hole at the center of our galaxy thus serves not just as an object of scientific study, but as a conceptual touchstone that continues to reshape our understanding of reality itself. The implications of Sagittarius A star for our understanding of reality connect directly to questions about how this extraordinary object came to exist in the first place. While we've explored its current state and future evolution, the origin story of Sagittarius A star remains one of astronomy's most fascinating puzzles. Tracing the formation and growth of our galaxy's central black hole requires us to look back through cosmic history, piecing together clues from observations, computer simulations, and theoretical models to reconstruct events that occurred billions of years ago. The birth of Sagittarius A star likely coincides with the earliest epochs of galaxy formation in the universe. After the Big Bang, approximately 13.8 billion years ago, the universe consisted primarily of hydrogen and helium gas with small density fluctuations. As gravity amplified these fluctuations, the first structures began to form. Within about 1 billion years, the earliest protogalaxies were taking shape, including the embryonic Milky Way. But how did Sagittarius A star itself form? Astronomers have developed several competing models that might explain its origin. One possibility is the direct collapse scenario, in which an extraordinarily massive cloud of gas in the early universe collapsed directly into a black hole without first forming a star. This process could have created a seed black hole with thousands or even tens of thousands of solar masses, providing a substantial head start on growth. Another possibility is that Sagittarius A star began as a much smaller black hole formed from the collapse of one of the universe's first generation of stars. These population 3 stars, formed from pristine hydrogen and helium without heavier elements, could reach masses hundreds of times greater than our Sun. When such a massive star exhausted its nuclear fuel after just a few million years, its core would collapse to form a black hole of perhaps 100 solar masses, much smaller than the present-day Sagittarius A star, but a viable seed for growth. A third scenario suggests that dense star clusters in the early Milky Way could have experienced runaway collisions, with many stars merging into an increasingly massive object that eventually collapsed to form a black hole. This process could potentially create intermediate mass seed black holes of thousands of solar masses without requiring direct gas collapse. Regardless of which formation channel produced the initial seed, Sagittarius, a star would have grown substantially over cosmic time through two primary mechanisms: accretion of gas and mergers with other black holes. In the early universe, gas was far more abundant than today, with massive cold flows streaming along cosmic filaments into forming galaxies. This gas-rich environment would have provided ample fuel for a young Sagittarius A star, potentially allowing periods of rapid growth. Evidence from other galaxies suggests that many supermassive black holes experienced their most rapid growth phase during an epoch known as cosmic noon, roughly 7 to 10 billion years ago, when star formation and black hole activity peaked across the universe. During this period, Sagittarius, a star, may have briefly resembled a quasar, an extremely luminous active galactic nucleus powered by a rapidly feeding black hole, though likely a relatively modest one compared to the most powerful quasars observed in other galaxies. The growth history of Sagittarius, a star, is also inextricably linked to the merger history of the Milky Way itself. Galaxy formation is a hierarchical process, with larger galaxies built up through the merger of smaller ones. Each time the young Milky Way absorbed a dwarf galaxy, that smaller galaxy may have contributed its own central black hole to the growing system. These black holes would eventually sink to the center through dynamical friction and merge with the existing central black hole, adding their mass to what would become Sagittarius A star. Recent discoveries of fossil stellar populations in our galaxy provide tangible evidence of this merger history. The Gaia Space Telescope has identified stars with distinct motion patterns and chemical compositions that appear to be remnants of galaxies consumed by the Milky Way, the most significant of these past mergers. With a galaxy astronomers have dubbed Gaia Enceladus, or the Gaia Sausage, occurred approximately 8 to 10 billion years ago. This substantial merger likely delivered a significant amount of gas to the galactic center, potentially triggering a major growth phase for Sagittarius A star. Interestingly, the relatively modest size of Sagittarius A star compared to supermassive black holes in other large galaxies suggests that the Milky Way has experienced fewer major mergers than many of its cosmic peers. With a mass of only 4.3 million solar masses, our central black hole is notably smaller than those found in comparably sized galaxies. This peculiarity may reflect the Milky Way's somewhat unusual evolution, with fewer major mergers but many minor ones over its cosmic history. The growth of Sagittarius A star wasn't necessarily steady over time. Computer simulations of galaxy evolution suggest that black hole growth often occurs in intense bursts when new material becomes available, followed by longer quiescent periods. Several lines of evidence support the idea that Sagittarius A star has experienced such episodic activity. including the Fermi bubbles, giant structures extending above and below the galactic plane that appear to have been inflated by an energetic outburst from the galactic center a few million years ago. As we piece together the cosmic biography of Sagittarius A star, we gain insight not just into this particular black hole, but into the processes that shape supermassive black holes throughout the universe. Each new discovery about our galaxy's central black hole, from its mass to its spin to its current accretion rate, provides another constraint on models of its formation and evolution, gradually bringing this ancient story into sharper focus. The long history of Sagittarius. A star also demonstrates the extraordinary timescales involved in cosmic evolution. The black hole has existed for the vast majority of the universe's history. Growing alongside our galaxy as cosmic structure has evolved from the relatively smooth early universe to the rich hierarchy of galaxies, clusters, dot, and superclusters we observe today. This perspective helps us understand Sagittarius A star not as a static object, but as a dynamic entity with a complex life story stretching across cosmic time. Recent advances in computer simulations have allowed astronomers to model the formation and growth of supermassive black holes with increasing sophistication, incorporating complex physics of gas dynamics, star formation, and feedback processes. As these simulations become more realistic and observations of the early universe improve with new facilities like the James Webb Space Telescope, our understanding of Sagittarius A star's origin story will continue to be refined and enriched. The ongoing investigation into Sagittarius A star's formation and growth represents just one aspect of the rapidly evolving field of black hole research. As technology advances and theoretical frameworks mature, the next frontiers in studying our galaxy's central black hole promise even more remarkable discoveries in the coming decades. One of the most exciting near-term prospects is the development of the next-generation Event Horizon Telescope, which aims to produce not just static images but dynamic movies showing the flow of material around Sagittarius A star's event horizon. By adding new radio telescopes to the existing network and implementing more sensitive receivers, astronomers expect to achieve higher resolution and collect data more quickly. This could potentially allow them to observe changes in the accretion flow over hours or even minutes, effectively creating a real-time view of the black hole's immediate environment. These improved observations will help resolve ongoing questions about the structure of Sagittarius A star's accretion flow. Current models suggest the presence of a relatively diffuse, hot accretion disk rather than the thin, dense disks seen in more active black holes. But the detailed structure remains uncertain. Dynamic imaging would reveal precisely how gas moves in this environment, potentially showing turbulent eddies, magnetic reconnection events, and other complex phenomena occurring just outside the event horizon. Another promising frontier involves multi-wavelength coordination, simultaneous observations of Sagittarius A star across different parts of the electromagnetic spectrum. By synchronizing observations from radio, infrared, X-ray, dot, and gamma-ray telescopes, astronomers can obtain a more complete picture of physical processes occurring at different distances from the black hole. For instance, a flare observed in X-rays might trigger changes in radio emission minutes or hours later as the energy propagates through the accretion flow, revealing connections between different regions of the black hole's environment. The Nancy Grace Roman Space Telescope and the James Webb Space Telescope will revolutionize infrared observations of the galactic center, potentially detecting fainter stars even closer to Sagittarius A star than currently possible. This could allow for the detection of small, fast-moving stars that experience stronger relativistic effects, providing even more stringent tests of general relativity in the strong field regime. Some calculations suggest that a sufficiently compact object on a close enough orbit might even allow detection of the black hole's spin-dragging effect on spacetime directly. Ground-based facilities will push boundaries as well. The upcoming Extremely Large Telescope, with its 39-meter primary mirror, will provide unprecedented resolution in the infrared, potentially resolving features just a few Schwarzschild radii from the event horizon. This enormous light-gathering capability could even detect the faint emission from hotspots in the accretion flow as they orbit the black hole, tracing out the extreme distortion of spacetime in this region. In the realm of high-energy astrophysics, proposed X-ray observatories like Athena, Advanced Telescope for High-Energy Astrophysics, will offer much more sensitive measurements of the hot gas near Sagittarius A star. These observations could reveal the detailed temperature structure of the accretion flow and potentially even detect X-ray echoes as radiation from flares reflects off material at different distances from the black hole, providing a kind of X-ray tomography of the inner galactic centre. Perhaps the most revolutionary new window on Sagittarius A star will come from gravitational wave astronomy. While current facilities like LIGO and Virgo aren't sensitive to the low-frequency gravitational waves produced by objects orbiting supermassive black holes, the planned Laser Interferometer Space Antenna LISA will be scheduled for launch in the 2030s. LISA could potentially detect gravitational waves from compact objects, stellar mass black holes, neutron stars, or white dwarfs orbiting close to Sagittarius A star. These signals would provide an entirely new probe of the spacetime near the black hole, complementary to electromagnetic observations. Even more exciting is the prospect of pulsar timing arrays detecting the background of gravitational waves from supermassive black hole mergers throughout the universe. This technique uses precise measurements of radio pulses from rapidly rotating neutron stars to detect the subtle stretching and compression of spacetime caused by passing gravitational waves. As this method improves, it could potentially detect the gravitational wave background that includes contributions from the early growth phases of black holes like Sagittarius A star, offering a new view of their formation history. Computational advances will play a crucial role in these next frontiers as well. As supercomputers become more powerful, simulations incorporating general relativity, magnetohydrodynamics, and radiation transport can model the environment around Sagittarius A star with increasing realism. These simulations serve as both interpreters of existing observations and predictors of what new facilities might see, guiding the design of future experiments and the interpretation of their results. Quantum gravity remains perhaps the most profound theoretical frontier related to black holes like Sagittarius A star. While direct tests of quantum gravity near black holes remain beyond current capabilities, indirect approaches are being developed. Some models predict subtle deviations from general relativity that might be detectable in precise measurements of stellar orbits or in the detailed structure of the black hole's shadow. Others suggest that correlations in Hawking radiation might eventually be observable, though probably not from supermassive black holes due to their extremely low temperature. The search for intermediate mass black holes orbiting near Sagittarius A star will intensify as observational capabilities improve. Confirming their existence and measuring their properties would provide crucial insight into how supermassive black holes grow and would help complete our census of black hole populations throughout the universe. Public engagement represents another important frontier in Sagittarius A star research. The first image of the black hole captured public imagination worldwide, and future results will likely continue this trend. Interactive visualizations, virtual reality experiences, and citizen science projects related to Sagittarius A star are already being developed, allowing non-specialists to engage with and potentially contribute to our understanding of this extraordinary object. As these various frontiers advance, they will likely intersect in unexpected and synergistic ways. Discoveries in one area will inform questions and approaches in others, gradually building a more complete and nuanced understanding of Sagittarius A star and black holes generally. While we've made remarkable progress in understanding our galaxy's central black hole, the pace of discovery shows no signs of slowing. The coming decades promise to be at least as revolutionary as the past ones, continuing to transform our understanding of these extraordinary cosmic objects and their role in the universe.